Welcome back to che531. This is the last video on stability analysis and the accuracy comparison between the four methods we covered thus far, the forward, backward, Euler, trapezoidal method, and RK methods. In the last video, I showed you how to calculate the stability region for RK2 and RK4. Okay, so now if we compare all of them in like a table, we can have something like this. Let's say we have the methods in the first column, the forward, backward, Euler, trapezoidal method, and RK2 and RK4. This is the order of approximation. This is, so 1 here means O delta x, 2 means O delta x squared. We know that trapezoidal method and RK2 are both second order methods. And then 4 means O delta x to the fourth power, which means RK4 is the fourth order. And then the last column is the maximum step size that we can choose to be stable while we're doing or while we're solving the differential equation using the method. So in forward Euler, we know that all explicit methods are conditionally stable. Okay, so forward Euler is conditionally stable, and the condition is if lambda is less than 0, delta x should be less than or equal to 2 over lambda, absolute value of lambda. Okay, if delta x is bigger than that, then the method is unstable. For backward Euler and trapezoidal method, for these two, there is no limit because these are implicit methods, and we know that for implicit methods, they're unconditionally stable. So there's no condition on them. For second order RK method, if lambda is less than 0, the condition is 2 over lambda. So that means the delta x we can choose is identical to the delta x limit for forward Euler, beyond which the method is going to be unstable. Now this delta x can be a little bit larger for RK4, but still there's a limit. If the delta x is bigger than that, then the method becomes unstable even for RK method, RK4, which is fourth order, which is really more accurate than anything else here. Okay. So now, speaking about the accuracy and order of approximation here, I'd like to show you a simple comparison by solving an example and see how basically these can be compared and analyzed in more details. Okay, so let me just skip through this and then go directly to the example we're going to look at. Let's say we have a dy dx equal x squared times y with the boundary condition of y at x equals 0 is 1. Okay, so we know the exact solution of this. I think we did this before. We can split the variables and bring all the y's to one side by dividing through by y and then multiply through by del x and have all the x on the other side. Okay, now we can integrate both sides, and integrate the left with respect to y and integrate the right with respect to x. So now we can have log 1 on the left side and 1/3 times x cubed plus some constant on the right side. The constant of integration can be found by applying the boundary condition. Alright, fine. So at the end of the day, we can calculate the y exact, which is going to be exponential of this. Okay. Now, we're going to solve the same problem, using the 5 methods we covered so far, and we're going to change delta x. We're going to lower delta x and measure how much error we're making. Because we have the exact solution, we can compare the numerical solution against the exact solution, find the error, and plot error as a function of delta x. Okay, so let me just show you the result first. So this is the result I was talking about. So here I'm plotting the error, the log of the error, right, against the number of discretization, or you can think of basically number of points along the domain. Okay. So as we increase more points, which means we're using less delta x, then the error is going to go down. You see that on all of them, I see error starts from something large and then goes down as number of discretization goes up. Okay. So from blue to red, black, pink, and green, we're testing forward Euler, backward Euler, RK24, and trapezoidal method. Now, with this discretization, I can go ahead and calculate my delta x. So on the right panel now, I'm showing the same error, but against the delta x. Like for this point, okay, delta x is going to be, let's say, the total domain divided by 10 points. For this point, delta x is going to be the total domain divided by 20, because they're 20 points. And let's say for this point, delta x is going to be the total domain, the length of the domain, let's say from 0 to 1. Then the total length of the domain is going to be 1 divided by 100, because we have 100 points, or 100 intervals. Okay. So now we get, using that, we're going to get the right curve, or right figure. So now by looking at it, you see that the slope of red and blue, the slope is 1. Why? Because it goes down by 1 unit, and it goes across this by 1 unit. I mean, in the log scale, this is 10 to the 1, is 10 to the 2. So the log of it is going to be 1 unit, right? So 2 minus 1 is just 1 unit. From here to here is also 1 unit. So the slope of this in the log scale is 1. That means the method is O delta x. Okay, so these two are both delta x. That's why the slope is 1. Now, these two have slope of 2 because they go down by 2 units almost. So from this point to this point along the y-axis, like 2 units. And along the x-axis is still 1 unit. So the slope is going to be 2 by 1 is just 2. So in the log scale, the slope is 2, which means that's O delta x squared. And we knew this from before, trapezoidal method and RK2, both of them are second order. Now this last one, the pink one, is RK4, which means the slope better be 4. So now along the y-axis, we go down by 4 units in the log scale, right? And along the x-axis, we go forward by 1 unit. So the slope of the pink line is going to be 4 by 1, which is 4. Okay, so that means RK4 is O delta x to the 4th power. So by just looking at how the error goes down as a function of delta x in the log scale, the slope of the curve is going to be the order of approximation. Okay, so again, slope here is 4, it's O delta x to the 4th power. Slope here is 2. But forget about the negative sign. I know the slope is minus 2, but let's say the absolute value of it is 2. Okay, the slope is 2, which means O delta x squared, and here slope is 1, which means O delta x. Okay, so this actually explains how we can figure out the order of approximation by plotting the error as a function of delta x. Okay, so in the next few minutes I'm going to talk about one example for which actually the stability analysis can help. So the example we're going to look at is a very practical example. It's a pendulum problem. Let's say I want to solve this pendulum problem, which has differential equation like this. Is the so the second derivative of theta, which is the angle, the deviation from the vertical line. So basically I have a pendulum. If I move the pendulum, to the left or right and leave it, then the pendulum is going to oscillate. If there's no drag, it's always going to oscillate forever. But if there's a drag and friction with the air, the angle is going to go down over time, and then it's going to stop right along this vertical line. So the governing equation for this motion is like this: is the angle, the second derivative of angle with respect to theta, so this angle, is going to be minus g, which is the gravity, times the sine of theta divided by L, which is the length of the pendulum. Okay? So our goal is to find theta as a function of time. We're going to solve this numerically using one of the techniques, or maybe 4 techniques we learned so far: RK24, trapezoidal method, and Euler method. Okay, so this is actually a nonlinear differential equation because it is nonlinear with respect to theta, right? So we have sine theta here, not just theta. And so this nonlinearity needs to be taken care of. And the way we do this is, so that's number 1 actually. The second thing is, this is a second order differential equation. It's not first order. Everything we learned so far was just dy dx equals something. And this is the second derivative, which needs to be converted to a first derivative differential equation. Okay. So to convert it to first order, we assume a variable called w. Let's say w is equal to the first derivative of theta. And if so, then w dot is going to be theta double dot, like that. And then theta double dot, by definition, is minus g sine theta over L. So now I can convert my differential equations completely over w instead of theta. Okay, the first equation we're going to have is going to be w dot, and that's equal to minus sine theta. Okay, let's say we assume g and L is 1 just for simplicity, right? So I know that these are numbers, but for simplicity, let's say these are 1. It doesn't change it. It's a technique we're going to use to solve a problem. Okay, and then if you have friction, we can have actually the friction proportional to the angular velocity squared. If w is the theta dot, which means angular velocity, then the faster the angular velocity, the more drag, or the more coefficient. So we can add it by just multiply beta, some friction coefficient, times the velocity squared. Okay, so that's going to be the second derivative of theta, or the first derivative of w. So that's one equation. The second equation is just the definition we had. W is equal to theta dot. So now I have 2 equations, right, with 2 unknowns, theta and theta dot. Okay, so I converted the second order differential equation in theta. Okay, I converted the second order differential equation to 2 first order differential equations. One is in theta, the other one is in theta dot. Okay, so the first equation is basically this equation, and that is, well, the derivative of theta with respect to t is going to be theta dot. I mean, this is just the definition we had. And then the second equation is the derivative of theta dot with respect to time is going to be theta double dot, and that's equal to minus sine theta minus beta, and then times theta dot times the absolute value of the theta dot, because w is theta dot. So now you see that I have a vector differential equation of theta dot as just one whole vector. Okay, it's the first order differential equation because this is just 1 d dt. And that's not linear because, you know, things depend on like sine theta and theta dot scores. It's a nonlinear vector equation. So we converted a nonlinear second order differential equation to 2 first order differential equation, but still nonlinear. Okay, how we can go and solve this? Well, now this is easy. We can assume this is y, so this is dy dt is equal to f of y. This is some function of y. Okay, so in the next video, we're going to look at how we can solve this vector equation using the 4 techniques we learned: the forward Euler, backward Euler, RK method, and trapezoidal method. So stay tuned for the next video on how to solve the pendulum problem. Thanks so much for watching.